video broadcast, you learned a little bit about describing motion, and we discussed this definition of speed. Speed is defined as the distance an object travels per unit of time. We also discussed the speed equation, which looks like this. Speed is distance divided by time. And we also derived these two other equations to calculate distance in speed. I also showed you how you could use the speed triangle to easily come up with all three of these equations, knowing that speed is distance divided by time, distance is speed times time, and then finally time is distance divided by speed. This speed triangle here is very handy and should help you be able to solve the problems quickly, easily, and accurately. The last thing that I want to make sure that you remember is that whenever we're describing motion, we describe speed using units of length divided by units of time. What these units of length are can be any of these listed plus many others, and the units of time are about the same. You have hours, minutes, seconds, days, but it could be as long as eons or as short as milliseconds. What I wanted to do was just spend a moment today discussing the difference between average speed and instantaneous speed. For most of what we do in our class, we will be talking about average speed. And we consider average speed to be the total distance divided by the total time. But I want you to be aware of the fact that there's this thing that we call instantaneous speed. And that's a speed that an object is going at a given instant in time. In order to calculate instantaneous speed, it does require the use of calculus, which we won't be doing here. However, what we can be doing is looking at different parts of an entire journey, if you will, and calculate the average speed for each of those individual parts. What that might look like is something like this. So again, let's consider you have your average speed is your total distance divided by your total time. Now here's an example of what instantaneous speed looks like. Let's take, for example, right here, your distance is equal to 0 and your time is equal to 0. And you're going to be traveling along in your little car and you're traveling along. And after the first hour, you've traveled a distance of 20 miles. And you're going to keep traveling along for another hour. And by then, your distance will be 60 miles. Well, what we can do is we can calculate the average speed for the different legs of your journey. This area from here to here is what we'll call leg 1 of your journey. And this area right here is what we're going to call leg 2 of your journey. So knowing that, we can calculate the average speed for not just the first leg and the second leg, but for the entire journey itself. Okay, so let's do some of these calculations. So the first leg of our journey, our car starts at distance 0 times 0, and it ends of distance 20 miles time 1 hour. So I'm going to write my average speed as total distance divided by total time, 20 miles divided by 1 hour, and I'm going to end up with an average speed of 20 miles per hour. Now for leg 2 of the journey, I'm going an additional 40 miles because I'm going to start out at mile marker 20 and I'm going to end up at mile marker 60. So that's a difference of 40 miles. And it took me 1 hour to travel that amount of time. So I have 40 miles divided by 1 hour. And that's going to give me an average speed of 40 miles an hour. Now the last thing that I'd like to do is we're going to calculate the overall average speed. So here we are, this is when we started at time point 0 and we drove along and we drove the whole 60 miles and it took us 2 hours to get there. So average speed being total distance divided by total time, we have 60 miles divided by 2 hours, and that gives us an average speed of 30 miles per hour. So understanding how average speed is calculated can help us when we're doing parts of a trip or the entire trip all put together. To do next is show you how we can describe motion using speed graphs. Consider this word problem right here. Ashley rode her bike to Robert's house. It took her 15 minutes to go the first half mile, where she stopped to chat with her friend Sally for 5 minutes. The next half mile was a big hill. It took her 20 minutes to get to the top. When she got there, she rested for 5 minutes. The remaining half mile was all downhill, so she was able to get to his house in 5 minutes. So what I'd like to do is show you this graph that I have right here. First of all, you'll notice that I have along my x-axis time in minutes, and I have them at 5-minute intervals. On the y-axis, I have distance in miles, and I've done an interval of a half a mile. So let's just take a look at the word problem itself, and we can put some points on the graph that will represent all of the things that Ashley did on her way to Robert's house. First of all, it took her 15 minutes to go the first half mile. So here I am on the x-axis. I'm going to look for 15 minutes, and then I'm going to move up, and I'm just going to put a dot right at a half a mile. This is where she stopped to chat with her friend Sally for 5 minutes. So for 5 more minutes, that brings it up to 20 minutes, she was chatting, so she didn't go anywhere. Her distance didn't change. The next half a mile was a big hill. It took her 20 minutes to get to the top. So 20 minutes plus 20 minutes gives us 40 minutes. This is our total elapsed time, and she's gone a half a mile further. The next plot that I want to point is right here. When she got there, she rested for 5 minutes. So here we are at 45 minutes. She didn't go any further, so we're going to put a point right here at 1 mile. And then for the remaining half a mile, it was all downhill, and she got there in 5 minutes. So 45 plus 5 more minutes gives us 50 total elapsed minutes, and her total travel distance is 1.5 miles. What we could do is we can put some lines here to demonstrate, or not. Okay, there we go. So we can put some lines here to connect all of the points on this graph. And you'll see that we have a line graph that represents all the distance that she's gone. We can learn a lot by analyzing this line graph, and we're going to do exactly that on the next page. So here we have the exact same graph on the previous page. And when you did your wacky race course in integrated math, one of the things that you learned was this formula right here. Slope is equal to rise over run. When we look at our graph that we have here, rise is equivalent to the y-axis, which in this graph is distance. Run is equivalent to the x-axis, which is equivalent to time. So I can rewrite this formula, slope is equal to distance over time. Now I hope that this distance over time will look remotely familiar to you, and you'll recall that that is in fact the speed equation. As a result, we can rewrite the speed equation as being rise over run. So what I'd like to do is, using this graph that we have here, we can calculate Ashley's speed. So the first thing I'm going to do is look at the first segment of the ride here. If we look at rise, we could see that she traveled 0.5 miles. The run, again, is the time, and it took her 15 minutes. So we can write that problem as 0.5 miles divided by 15 minutes. Using my calculator over here, I can just go ahead and punch in 0.5 divided by 15, and I'm going to get the number 0.03 bar. So I'm going to go ahead and write that down here, 0.033, and keep in mind that our units for speed are miles per minute. Looking at the second leg of her journey, you'll see that she traveled 0 miles. So the rise in this case is equal to 0. There's no change in the distance. However, the time took 5 minutes. So I can rewrite this as 0 miles divided by 5 minutes, and I can go ahead and do the calculations and determine that she traveled 0 miles per minute. For the next segment, when she was going up the hill, the rise along here was the difference between 0.5 and 1, which is 0.5 miles. The time that it took her, she started at 20 minutes and she ended at 40 minutes, so that's going to give her a total of 20 minutes travel time. When we punch in the numbers again, we can find that 0.5 miles divided by 20 minutes is equal to 0.025 miles per minute. On the next leg of her journey, when she was resting at the top of the hill, she had no change in her distance. She wasn't moving. So the rise in this case is going to be 0. The run is going to be a 5-minute time period. She started at the 40-minute mark. She ended at the 45-minute mark. So that gives us our formula right here, 0 miles divided by 5 minutes. As a result, her speed is 0 miles per minute. And this makes sense because she's not going anywhere, so her speed should be 0. For the last leg of her journey, she traveled the 1 mile downhill, and she did this in a 5-minute time frame. So I'm going to go ahead and I'm going to write rise over run, which is 0.5 miles divided by 5 minutes. Her speed here is 0.1 miles per minute. So what I'd like to do is just take a minute and I'm going to compare all of these speeds to the slopes on the graph. You can see here at 0.033 miles per minute, it's going up at a steady pace. At 0 miles per minute, it's not moving at all. The slope is 0. For this section right here, her speed is 0.025 miles per minute. You can see that the slope is not nearly as steep as what she had in the beginning. Again, 0 miles per minute, it's a flat line with 0 slope. And then finally, when she was traveling at 0.1 miles per minute, you can see that the slope is fairly steep. So what we can learn from all of this is just by looking at a distance time graph or a speed graph, we can not only calculate the exact speed that they're traveling, but you can look at relative speeds. For example, this very steep line is a lot faster, 0.1 miles per minute is faster than this flatter line that we have right here, which is 0.025 miles per minute. In class, we'll be creating more of these speed graphs and interpreting more of these speed graphs.